Today we're going to talk about logarithmic graphs and inverses. Because logarithmic functions and exponential functions are inverse functions, the characteristics of their graphs will have inverse relationships. So logarithmic function has a general form f of x equals a times the log base b of x when b is greater than 0, where a and b are constants with a not equal to 0 and b not equal to 1. So looking at your graphs, you can see that the domain is going to be from 0 to infinity, and the range is all real numbers. And this kind of goes along with our exponential functions and the graphs we talked about, because remember, these are inverses. So logarithmic functions are always increasing or always decreasing. They will never switch from one to the other. So they don't have a relative or local extrema unless on a closed interval. Concave up versus concave down. Logarithmic functions are always concave up or always concave down. They will never switch concavity, so they have no points of inflections. So if we also look at these, remember that our exponential functions have a horizontal asymptote, so our logarithmic functions have vertical asymptotes. So there's a vertical asymptote here and here on our graph. So I'm just going to write that out. So vertical asymptote at x equals 0. And you can see that this graph is bending downwards, so this is concave down. And this one over here is concave up. So the end behavior for logarithmic functions in general form, as the input values x increase without bound, the output values y will increase or decrease without bound. Since logarithmic functions have a restricted domain, they are vertically asymptotic to x equals 0. As a result, the left end behavior will occur as x approaches 0 from the right side. So end behavior limit statements are going to look somewhat similar to these. So, and we'll talk about this more in the next couple of examples. So it says, write the limit statements for the end behavior of the following logarithmic functions. So if we're looking here, we can see that, again, there's that vertical asymptote at x equals 0 right here. And as the limit as x approaches 0 from the right side. So notice that we can't go to negative infinity because we have that vertical asymptote there, because remember, we cannot ever touch or cross over a vertical asymptote because it's where a graph's undefined. So in this case, we're saying as our x values approach 0 from, remember that plus sign means from the right, so the right side approaching 0, our y values are going towards negative infinity in this case. And then the limit as x approaches positive infinity. So as our x values get larger and larger in the positive direction, your y values are going to be slowly increasing to positive infinity. For this graph, this looks like we reflected it across the x-axis, but you can still see that we have our asymptote right here, vertical asymptote at x equals 0. So the limit as x approaches 0 from the right, again, now is going to positive infinity, and the limit as x approaches infinity, the y values are going then towards negative infinity. And for C, so if we think about this logarithmic graph, so 2 log base 3 of x. So our log graphs, we know go like this, like that first graph that we have of A. And in this case, we're doing a vertical stretch by 2. So we're just graph's going to be going again like this. You don't change your vertical asymptote unless you're moving your graph left or right, which we'll be looking at. So in this case, the limit as x approaches 0 from the right side of g of x, because that's the name of the function, is approaching negative infinity. And then the right limit would be the limit as our x values are going to increase towards infinity for g of x, is going towards positive infinity. So then for the next ones, it says for each of the following, determine if the logarithmic function is increasing or decreasing, and concave up or down. So looking at this graph right here, we can see as we go from left to right in our graph, our y values are decreasing. And then the curve, notice it's bending upward, so this would be concave up in this case. For the next one, the curve's bending downward, so concave down, and our y values are increasing from left to right, so this would be increasing. And then the next one, we have to think about our transformations. So here our a value is less than 0. And again, if you forget the graphs, if your a value is greater than 0, it's going to go like this. Less than 0 goes like this because, again, that's a reflection across the x-axis. If you want to make a note to reflect across the x-axis. So that's why it's going the other way. So looking over here, we know a is less than 0. We haven't moved our graph left or right, so I know my graph is going to be going something like this. So this is going to be, in this case, concave up because the curve is going to be bending upwards. And then our graph, you can see from left to right, the y values are decreasing, similar to our first graph that we had. So this one says to find the inverse equation. So we know that for this, we have y equals 10 to the x. So when we want to find the inverse, we switch our x and our y. So x equals 10 to the power y, and then we solve for y. But remember, how do we solve for a variable exponent? The way that we do that is we use logarithms. We learned that last year in Math 3. So this would be the log of base 10 of y, or excuse me, of x, equals y, because remember the answer to a logarithm is an exponent. And we can see then on our graph here, we have it graphed in this red color. And so for this graph, we also know that we have a vertical asymptote at x equals 0. And looking at this graph as well, this is for the, my bad, sorry, this is for the exponential function. So the other one, the vertical asymptote's for the logarithmic. So I'm going to write that over here. So vertical asymptote is at x equals 0. And for our exponential function 10 to the x, our asymptote is horizontal. So this would be a horizontal asymptote at y equals 0. And so again, it makes sense that if we have a horizontal asymptote for our exponential function, our logarithmic function would be a vertical one because you switch your x and your y values. So let's go ahead and find the inverse of our logarithmic function. So we have x equals the log base 10 of y. And remember, when the base is not written with the 10, we know that it's 10's common logarithm. And then we're going to rewrite this in exponential form. So 10 to the power of x equals y. So that would be the inverse equation. And so going back to my exponential equation, if I make a table of x and y, so if I plot -1, let's say for x, and I plug that in, I get 1/10. If I plug in 0, 10 to the 0 power is equal to 1, and 10 to the first is equal to 10. So on my inverse graph, we would have 1/10, -1, 1, 0, and 10, 1. So that's just looking at those graphs. And then, of course, we can find the domain and range. We already talked about that in the first graphs. So now we're going to look at finding inverses of exponential and logarithmic functions in general form. So these are the general forms right here. So I just put base because the base will change depending on the problem. So it could be a base of 2 or a base of 3 or a base of 1/3. And so whatever that base is, remember that base for the inverse also stays the base here. But these are the general equations for exponential and logarithmic functions based upon the transformations. So we can find the inverse of y equals f of x by determining the inverse operations to reverse the mapping. So finding the inverse of logarithmic and exponential functions, we switch our x and y's in the equations. We use inverse operations to solve for y and the inverse relation. So we're going to use, again, when you're solving, you do PEMDAS backwards. And then we're going to write the final inverse function using the correct notation. So here, notice that for example A, we have an exponential equation. So we know that our final answer should end up being a logarithm, whereas question B is a logarithmic equation. So if we were doing the inverse equation, we know we should end up with an exponential because they're inverses of each other. So for this, we have x equals 3 times 1/2 to the y power minus 7. So remember, when we're solving, we're going to do PEMDAS backwards. So we want to get rid of things added to subtracted, then multiplied, divided, then the exponent, and then the parentheses. So here, we don't just go ahead and rewrite this in logarithmic form now because we have to isolate this part of our equation first. So this is the exponential part of our equation, the base with the exponent. So we do that by first adding the 7. And we get x plus 7 equals 3 times 1/2 to the power of y. And then the next step is going to be to, again, isolate the exponential expression. So then I'm going to divide by 3. So now we have x plus 7 over 3 equals 1/2 to the power of y. Now that I have isolated the base with the exponent, now I can go ahead and rewrite this in logarithmic form to get the variable exponent out of the exponent. So then this would be the log of 1/2 of x plus 7 over 3 is equal to y. So that's why we like to use logarithms, is because it allows us to get that variable exponent down so it's no longer a variable exponent. And then, of course, going back to up to here where we had our logarithmic function general form, I'm going to go ahead and write it in that form. So I'm going to make this a little bit smaller so I have room to write. So if I write it in that form, notice that your b value is in front, factored out. So this would be, actually, I'll write it down here. So we have f inverse of x is equal to the log base 1/2 of, and so this would be parentheses with the 1/3 close parentheses x plus 7. And then that would be our solution. And again, so notice that our b value here is 1/3. And if I were to distribute that back, I would get 1/3 x plus 7/3, which is what we have right here, x over 3 plus 7 over 3, because the 3 is being divided by both. It's just a different way of writing it. But we're going to write it in this general form right here. So this would be my inverse equation. So then looking at question B, so this is a logarithmic equation, so we know the inverse should end up being exponential. So same idea, we want to get rid of things added or subtracted, then multiplied or divided, then parentheses, exponents in parentheses. So right here, remember that a logarithmic function, the answer to that is the exponent. So that means that first we want to isolate this log before we can rewrite this in exponential form. So we're going to first get rid of things added or subtracted. And actually, before I do that, I need to switch my x and my y's. This would be x minus 10 equals 5 log of 3y. And then again, we're trying to isolate the log. So then divide by 5. So I'm going to rewrite this as x over 5 minus 10 divided by 5 is 2 equals the log of 3y. And so remember, when the base is not written, we know this is a base of 10. So this would be, now we can rewrite this in exponential form because we've isolated the log in the argument of the log. So this is going to be 10. And then remember, the answer to log is the exponent. So I'm going to rewrite this as 1/5 x minus 2 equals 3y, and then we're going to divide by 3. And so for this, we would get f inverse of x is equal to that 10 over 3 can't divide, so really that's your a value. So this would be 1/3 times 10 to the 1/5 x minus 2. So this would be our answer with the b in not in factored form. But if we write our answer with that b in factored form, it would be f inverse of x is equal to 1/3 times 10 to the 1/5 times x minus 10. And then we don't really need that parenthesis there, so we just write like this. So that would be the other way. You can write this if you leave the b value in factored form, or if you distribute it, that's fine too. So you can write it either way. And over here, we could have, like I said, written this as 1/3 x plus 7/3, the same thing. But if we're rewriting it in the form with the general form right here, notice it's in the factored form. And that's good to leave it in the factored form for when we get to our transformations. So next we're going to talk about graphing logarithms. We talked about this last year in Math 3, but when graphing logarithmic functions, it helps to graph the 3 reference points. So the 3 reference points for y equals the log of some base b, we're calling it, of x. So we use that b to help you write your points. So it's going to be the 1 over the base, comma, -1, and then 1, 0, and then the base, comma, 1. These 3 points are going to help you make graphing a little bit easier. So looking at this first one, y equals log base 4 of x. So for this equation, we would have a base of 4, so 1 over 4, comma, -1, 1, 0, and then the base, which is 4, comma, 1. So what are we doing when we're doing that? We're doing y equals the log base 4 of 1/4. And then this one right here is y equals the log base 4 of 1. Y equals the log base 4 of 4. And so if it helps, remember 4 to what power equals 1/4? Well, -1. 4 to, and I guess I should use the y because I have e equals to y. So 4 to the what power equals 1 to the 0 power. 4 to what power equals 4, full 4 to the first. That's why we have those 3 points that work. So we have 1/4 -1, 1, 0, and then 1, 2, 3, 4, 1. And then we have a vertical asymptote. Anytime you're graphing these, always graph your asymptotes on your graph as well. So that would be my graph. And if my graph went further, because this is a base of 4, I'm going to think about powers of 4. So for powers of 4, we know 4 to the first power is equal to 4. That's why we have the 0.41. So if I was graphing another point here, the next point would be 4 squared, which is 16, so 16, 2. So looking at the next one, let's go ahead and look at number 6. We'll come back to question B, or sorry, I said number 6, question C, which is the log base 6, and then we'll come back to question B. So over here, the base is 6, so 1, 6, -1, 1, 0, and then 6, comma, 1. And then if I was to graph another one, because this is log base 6, well, think about powers of 6. So 6 to the first is 6. 6 squared is 36. So the next point would be 36, 2. Because remember, it's an inverse exponential. So you're just switching your x and y's when you're thinking about that. So we have 1, 6, -1, 1, 0, and then 1, 2, 3, 4, 5, 6, 1. And then again, we have that vertical asymptote at x equals 0. So I'll write that over here too. Looking at then the next one, we have a slightly different problem because notice the base is now a fraction. So for this one, if we have 1 over the base, so 1 over 1/3, comma, -1, we don't want to leave our fraction like that. So what is 1 over 1/3? Remember, when you have a fraction divided by a fraction, you keep, change, and then flip. So that's actually 3. So this would be 3, -1. Then we have 1, 0 still, and then the base, comma, 1. So 1/3 the base, comma, 1. So this one's slightly different because our base is a fraction. So we have 1/3, 1, 1, 0, and then 1, 2, 3, -1. So our graph is actually going like this. So it just goes the other direction. It should again make sense because if you think about your inverse function would be a base of 1/3, which is exponential decay. So that's why our graph looks slightly different, but we still have a vertical asymptote at x equals 0. If I was going to do another point for this one, I would use I think about base 3s. So I know that 3 squared is 9, but since this is 1/3, you would actually have the 0.9, -2. And you can kind of check that. So if I do the work over here, log 1/3 of 9 would be equal to -2 because 1/3 to the -2 is equal to 1 to -2 over 3 to -2. So 1 to -2 is going to just be 1 denominator. and 3 to the negative 2 gives us 9. So that you can see works out. So that's graphing using those 3 points. So then the next part, we have y equals a log of b times x minus h plus k. So the transformations we've talked about before, we know that our b value, if it's greater than, the absolute value is greater than 1, it's a horizontal compression by 1 over b. If it's in between 0 and 1, horizontal stretch. And I forgot to write on here, but of course if b is less than 0, then it reflects across the y-axis. And then h moves it left or right, which changes your vertical asymptote. And then if your a value is bigger than 1, vertical stretch by absolute value of a. If it's in between 0 and 1, vertical compression. If k is positive, it moves up. K is negative, moves down. And then of course over here, if a is less than 0, this reflects across the x-axis. So add those in. So let's go ahead and look at this example. It says graph y equals log base 2 of x minus 3 plus 1. So I'm going to think about the parent graph here. So the parent graph is y equals log base 2 of x. So our points that we're going to use, our reference points, would be 1/2, -1, 1, 0, and 2, 1. So 1/2, -1, 1, 0, and then 2, 1. But I have a whole bunch of graph over here, so I'm going to start graphing some other points. So again, think about your exponential form. So 2 to the x equals y. And for this, we're going to think about just switching the x and y's because we're doing the inverse when we're doing a logarithm. So we know 2 squared is equal to 4, so we have 4, 2. 2 to the third is 8, so this would be 8, 3. 2 to the fourth is 16, so 16, 4, etc. So if we did the next one, which would be 2 to the fifth, it's going to be off our graph because 2 to the fifth is 32. So 32, 5 would be the next point. So we have 4, 2, 8, 1, 2, 3, and 16, 1, 2, 3, 4. So this right here is the parent graph. And then of course we always want to graph our asymptote. So what are the transformations we are making to our parent graph? We're moving our graph to the right 3, because remember you always do b value first, then h, then a, then k. And somebody had said a good way to remember this, b would stand for big, hugs, and kisses. So Bach, so that's one way you can remember it. So right 3, and then we're going to move up 1. So if we move our graph right 3, we're also moving our asymptote right 3. So 1, 2, 3. So now our vertical asymptote is at x equals 3. And so I'm going to move all these points right 3, 1, 2, 3, up 1. And so our graph would look like this. I guess I should try to make that a little closer. All right, so that would be our graph. And so our asymptote, we can see the vertical asymptote at x equals 3. So our domain would be 3 to infinity. And the range for these is always all round numbers. All right, so let's look at the next examples. It says, describe the transformation from the graph of g of x equals log of x to the graph of h of x equals 2 log of x plus 4, then find the domain, range, asymptote, and behavior of h of x. So remember when the base is not written, it's a base 10. And so for this one, we're looking at the log base 10 and what type of transformations that we are making. So again, we talked about our general transformations. H of x is equal to a times the log base of something. So let's go I'm just going to write base here. We'll do 10 because we're using base 10 of b times x minus h plus k. So we know that we have no b value, it's just 1. So b is equal to 1, which doesn't stretch or compress or reflect our graph. Our h value is equal to -4 because it's x plus 4. To make that a plus, we have to have an h value that's negative. So that's going to move our graph to the left 4 units. And then our a value is equal to 2. which is a vertical compression by 2. BC by 2. And then there is no k value. So when there's no k value, it's just 0 because it doesn't move up or down when you have 0 there. So this would be none and then none. So BHAK would be the order of the transformation. So we just have these two right here. And then we want to think about the domain and the range. So another way to look at the domain, so you could think about this graphically if you want. So if we think about this graphically, we have our parent graph, which would have an asymptote here and look similar to something like this. Then if I move this to the left 4, that means that vertical asymptote is moving to the left 4. So now it would be here at x equals -4. And then that's 2 is just a vertical stretch. So it's just going to make our graph look like it's more upwards like this. So our domain would be then -4 to infinity. And the range for logarithmic functions is always all real numbers. Another way to think about the domain is that whatever you take the log of, as we said before, you can't take the log of a negative number or 0. So you can just take the argument of the log. So the argument of the log has to be greater than 0. So in this case, x plus 4 has to be greater than 0. So x has to be greater than -4. And again, if you think about a number line, -4, it's an open circle, number is greater than 4, go this way. So that's another way to think about finding the domain. The asymptote is a vertical asymptote at x equals -4. And then we're going to write the end behavior. So the end behavior, let's look at the left and the right. So in this case, we don't really have a left side of the vertical asymptote, but the left limit is just as we're approaching the vertical asymptote, what's happening. So the limit as x approaches, and now we're not approaching 0. Remember, we moved our vertical asymptote. So it's the limit as x approaches -4, and we're going from the right side of that vertical asymptote, because remember, this is the left side, this is the right side. And that plus means the right of the function, which is h of x, is going towards -infinity. And then the limit as x approaches infinity. So as our x values get larger, our y values are going towards infinity. So that would be our end behavior. All right, so last one, the natural logarithmic function we talked about before. It's just log with a base e, which we call natural log. So instead of saying log base e of x, we use the natural log of x. So in the next one, we're using the natural log of x as our parent graph, and then this is our transformed graph. So for this one, the first thing I would do is rewrite this and factor out that b value. So h of x is equal to the natural log of -x plus 2 minus 3. So this would be h of x equals the natural log, factor out that -1. So -1 times x minus 2 minus 3. So in this case, we have a b value. So our b value is -1, which reflects across the y-axis. And then our h value is equal to 2, which moves our graph to the right 2. A is equal to 1, which does nothing. There is no a value to do anything. We're not stretching or compressing vertically or reflecting across the x-axis. And then our k value equals -3, which is down 3. So for this one, if we want to figure out our domain, let's take the arguments and set it 2 minus x is greater than 0. So then -x is greater than -2, and divide by -1. So remember, whenever you divide both sides of an inequality by a negative number, you also have to switch the inequality sign. So this would mean that our x values are less than 2, which goes this way. So our domain is going to be -infinity to 2, parentheses, which makes sense because we had a reflection across the y-axis. Range is always all real numbers. So the asymptote here is at a vertical asymptote at x equals 2. So let's go ahead and draw a quick sketch of our graph. So the natural log parent graph would look something like this. So that would be the parent graph. So we're taking this parent graph and we are reflecting it across the y-axis, which means it would go this way. And then we're going to take that graph and move that graph to the right 2 and then down 3. So I'm just going to draw another one so it doesn't get too confusing. So if I move the asymptote right to 2, it would be here at x equals 2 and down 3. So our graph is going to go something like this. So for the left limit, our limit as x goes towards the left side would be going to a negative infinity. For h of x is equal to, and it's going up towards positive infinity. And then the right limit is going towards our vertical asymptote. So the limit as x approaches 2, and notice that this again is the right side of the vertical asymptote, this is the left, so we'd actually use a minus there. And again, that's because of that reflection of h of x is going down towards negative infinity. And that is it for our logarithmic functions, the inverses, and looking at the end behavior of the graphs.